All right, so chapter 2 here is going to talk about the atmosphere as a whole, a little bit about its origins, a lot about its composition and structure. So, what is the composition of the atmosphere? Well, the atmosphere covers the whole world. So, what happens in one part of the atmosphere impacts other areas. And they're given a case in point here of where dust comes from Africa into the United States. Actually, it's occurring right now. There's dust moving across from the Sahara into the southern, southeastern United States, particularly Florida. Some Caribbean islands, such as Puerto Rico, are reporting visibilities like a quarter mile of dust. That dust came all the way from the Saharas. So, what happens in one part of the world has an impact in another part of the world. So, you can see here the quality of the air worsens when this dust moves across, and weather can change quickly. It can be beautiful outside, and then all of a sudden, pouring down rain. Uh, we're going to talk a little bit about the Earth system here. The Earth system, when you look at the Earth as a whole, is composed of the atmosphere, which is what we're going to spend most of our time in, the hydrosphere, which is all the water around the world. Think about all the oceans out there, the lakes, the rivers. They're the hydrosphere. Geospheres, things like rocks, mountains, volcanoes. And then finally, we had the biosphere. That's us. Plants, animals make up the biosphere. So if you looked at the Earth as a whole, each one of these is part of the whole system. And the atmosphere is impacted by each one of these. In other words, the hydrosphere brings moisture in. The geosphere, the volcanoes and all spew ash into the air, which impacts the weather. The biosphere, plants. I can give you an example out in the Midwest in Oklahoma, where winter wheat grows in the spring, causes the air to be significantly more moist during that time of the year than later in the year after the wheat's harvested, as an example of the biosphere influencing the atmosphere. So we have very thin layer. You think about the atmosphere. Uh, Almost half of the mass of the atmosphere is within 18,000 feet, less than 3 miles. A lot of you all could probably run that, right? Uh, so if you could all run straight up, we could get through most of the atmosphere in just a few minutes. 99% of the atmosphere is 20 miles up into the air. So it is not a very thick layer when you think about how thick the Earth is all the way across. And the atmosphere, through most of its depth, is very, very uniform. In other words, nitrogen makes up 78%, oxygen 21%, and the other gases smaller percentages. And if you were up at Mount Everest, the oxygen would still be the same percent as it is on the ground. However, there's a lot less molecules of air up there, so you don't have as much oxygen. But the percentages are exactly the same. And here you can see that. There are other things that are in the air as well. Water vapor, typically less than 4%, and almost all of it is in the lowest 1 kilometer. Uh, Carbon dioxide in the atmosphere, aerosols, there's dust, uh, there's volcanic eruptions, and all of this impacts radiation, which impacts a lot of the atmosphere. Pollution is out there, most of it's man made. So when we study the atmosphere, we use something called the scientific method. So, what is that? Well, we like to ask questions. We want to know why something occurs. I'm going to give you an example that I worked on. It's where thunderstorms many times will move into the Appalachian Mountains from the west. Many times they weaken. However, there are other times when all of a sudden they strengthen and get significantly stronger when they move across the mountains and get onto the east side of the mountains. So we wanted to know why. We worked with North Carolina State University and posed that question. We formed a couple hypotheses. What parameters in the atmosphere might cause this to happen? So we tested those. If first couple times didn't work too well, we had the wrong parameters. We switched it up, tried some other ones, and all of a sudden we were able to replicate and produce results that corresponded to reality. So we were able to learn from this that we need these things for thunderstorms to continue to intensify when they come on the east side of the Appalachians. If we don't have them, thunderstorms will likely decrease. That helped us forecast for the people that live there. Here you can see an example of how some of the atmosphere is modeled. We have physical models like Purdue's vortex chamber. We have numerical models where we put equations together, develop from that computer algorithms to try to forecast what's going to happen in the future. I have a little issue with that, unfortunately. No mathematician can solve the equations that represent the atmosphere. So everything we do is an approximation. We have to observe the atmosphere. So how do we observe it? Well, one of the tools we observe are at airports. Almost every airport in the United States has a system called ASOS. What is that? It's a series of instruments that measure temperature, dew point, wind speed, clouds, visibility, all of that, precipitation, type of precipitation. And literally, it's measured every 5 seconds. So we have a continuous feed at the airports, not everywhere, of what the weather is. We also have the National Weather Service Cooperative Observer Network. It's a volunteer network pretty much. It's nobody's paid for it, but what we get are daily readings of precipitation, max and min temperature. They're used over the terms of months to look at climate and to look at agriculture to see if there's drought. Another source is COCORAS, where volunteers measure all the different types of precipitation and hail, also whether there's severe weather or not. We want to know a three-dimensional picture of the atmosphere as well. In order to do that, we need something that's going to tell us what conditions are in the upper atmosphere. We send up balloons. They burst at about 100,000 feet up approximately, but they're filled with helium, and as they go up, they record temperature, pressure, dew point, wind, speed, and direction. All of that to give us a vertical profile of what the atmosphere is like. And here you can see the small instruments that go up there. Dropsonde, it's exactly the same instrument pretty much, except it's dropped out of an airplane. So yes, it's getting a vertical profile. It's just starting at the top and going to the ground. These are very plentiful in hurricanes, helping to forecast those. Remote sensing. If I am not at the location of the weather, say I'm in the middle of Ohio and the thunderstorms are occurring, maybe or rain's occurring in southern Ohio, how am I able to understand or know what's going on down there? Tools like satellites, where you see the clouds in the sky, you look at what they look like, how much moisture is there, radar, are all remote sensing. They record different wavelengths of energy in order to tell what's happening away from where you are. So they're remote. Here is a temperature profile. And notice this is the profile through the whole atmosphere. So we have a tropopause, a troposphere. Troposphere, temperature's decreasing all the way up to the tropopause. And at the tropopause, it begins to warm. So that is where the stratosphere begins. Then it begins to cool off again in the mesosphere. And finally, in the thermosphere, it begins to warm back up again. These are the different layers in the atmosphere. All weather is pretty much confined to the troposphere. So that is the area we're going to spend our time and focus on. And there's another part of what we're going to talk about this week is auroras caused by the solar wind. The solar wind is just magnetic particles being sent out from the sun. They develop a magnetosphere around the earth, which protects the earth from these nasty particles, but at the same token causes things like the auroras and all that. So that is what we're going to discuss. This was just an introduction to the atmosphere as a whole right here. So I hope you got something out of that. And again, let me know if you have any questions.